Okay, so in today's class we're going to continue with chapter 2, which is measurements in chemistry. We're going to begin with a little bit of a review of scientific notation, and then we're going to move into a new topic, which is the use of conversion factors to convert between units within the same system of units, and converting between using conversion factors to convert between different systems of units. So English to English conversions, metric to metric conversions, and English to metric conversions, and vice versa. Related to that topic is the idea of dimensional analysis, which is the way that we can use the units within numbers that we have measured and that we're performing calculations on to assist us in the calculation. And then we're going to talk about the use of density as a conversion factor to convert a measurement that is in grams into volume, or a measurement that is in volume into grams. And then finally we'll talk about temperature scales and how they are interrelated via several formulas. So when we write a number in scientific notation, we have a term that has one digit to the left of the decimal point, followed by the required number of digits to the right of the decimal point to accurately depict the number of some significant figures. And then we have a exponential term, which is a power of 10, and this term out here is the exponent of the exponential term, and that indicates to what power of 10 that we're raising the number. So we have the coefficient, we have the exponent, and the exponent determines the exponential term, which is the power of 10 that we are multiplying our coefficient by. And scientific notation is very useful because when we express numbers in decimal notation with very big numbers with a lot of trailing zeros, that's prone to error, or very small numbers with a lot of leading zeros, again we're likely to make an error. So scientific notation is very useful for making it clear exactly what our number is. So to convert between scientific notation and decimal numbers, the decimal point is moved to the position to the right of the first non-zero digit. So we always have just one digit to the left of the decimal point. So in this case, 5015 is my number, and I need to move the decimal point 1, 2, 3 spaces to the left. So because I moved my decimal point to the left, then my exponent will be a positive number, and as I moved it 3 spaces to the left, then the exponent will be 3. So expressing 5015 in scientific notation, I would write 5.015 times 10 to the 3. So 1000 times 5.015 is equal to 5015. When I have very small numbers, I do the same procedure, but this time I will move the decimal point towards the right, and the number of spaces that I need to move the decimal point to the right, that will be expressed as a negative number in the exponential term here. So the exponent, when you whip for very small numbers, is going to be a negative number. So 3.4 times 10 to the minus 3, or alternatively 3.4 times 1/1000th equals 0.0034. So in scientific notation, only significant figures are included in the coefficient. So this number here has 3 leading zeros that are not significant and 2 non-zero numbers that are significant, so our coefficient has 2 significant figures. In this case here, I have 2 non-zero numbers that are significant, and I've got 4 non-zero numbers that are not significant, so the coefficient in the scientific notation has 2 significant figures. So now we move on to the topic of conversion factors. And so conversion factors are derived from equalities, and an equality is the relationship that describes the two sets of units. So for example, 1,000 millimeters is equal to 1 meter. That's the equality describing the relationship between millimeters and meters. And we can rearrange this equality to get two conversion factors, one in which millimeters is in the numerator and one in which meters is in the numerator. But because these two numbers are equal, they just differ by the units, this conversion factor is equal to 1 and this conversion factor is equal to 1. So multiplying a number by one of these conversion factors doesn't change the size, or multiplying a measurement by one of these conversion factors doesn't change the size of that measurement, but it will alter the units. So let's do an example. We use a conversion factor that divides by the units we wish to cancel and multiplies by the units that we want. So if I wanted to convert 1400 millimeters into meters, I would need to multiply by the conversion factor that had meters in the numerator and millimeters in the denominator. So here we are, 1,000 millimeters equals 1 meter is our equality. Rearrange that to get the conversion factor with meters in the numerator and millimeters in the denominator, and then multiply by our measurement that we want to change the units on. So 1400 millimeters multiplied by 1 meter per 1,000 millimeters, and the units of millimeters will cancel out, leaving our units of meters remaining. And so this concept of leaving the units in while we're doing the calculation and treating them like algebraic terms and cancelling them out, this is what is referred to as dimensional analysis, and it's a really great way of making sure that you have performed the calculation correctly and you know that the units in your final answer must be meters. So I would recommend leaving the units in and doing this dimensional analysis in all of your calculations. In this case, this 1400 millimeters here has two significant figures. Conversion factors never limit the number of significant figures in an answer, so our answer, we want it to be expressed as two significant figures, so 1.4 meters. Please circle your answers to make it obvious what it is that you consider to be your final answer. That helps me with the grading. Okay, so conversion factors used within the metric system of units are based on prefixes we discussed earlier. So these are the conversion factors that we're going to use to move between one measure in the metric system and another measure within the metric system. So we'll use things like 100 centimeters per 1 meter, 1 kilometer per 1,000 meters, 1 micrometer per 1 by 10 to the minus 6 meters. And because these conversion factors arise from unit definitions, there is no uncertainty about them. They are exact numbers and they do not impact the number of significant figures of the measurements that we are using them on. Okay, so many of you will have knowledge of conversion factors within the English system of units. For example, that 12 inches is 1 foot, or 3 feet is 1 yard, or there are 4 quarts in a gallon and 16 ounces in the pound. And these are what we will use to convert between different units of measure within the English system. So again, these conversions are exact numbers because they arise from the definitions of the units. There's no uncertainty associated with them. Multiplying a measurement by one of these conversion factors will not affect the significant figures in our answer. So one of the situations where people often get hooked up is in doing unit conversions regarding time. And the reason is because time's not a decimal based system. It's a little bit like our English units that are not a decimal based system. So for example, converting weeks into seconds you'll need to use more than one conversion factor normally. So here we go. I'm given two equalities to answer this question. I know that 1 day equals 86,400 seconds, but I don't know how many seconds are in a week. So I'm going to have to use a second conversion factor that converts from weeks to days. So I'm going to use two conversion factors here. So 2 weeks, the first conversion I'm converting to days. So I've got days on the top, weeks on the bottom, and that's going to get me to days. And then my second conversion factor needs to convert from days to seconds. So I've got seconds on the top and days on the bottom. So my first conversion factor results in the elimination of the weeks here and conversion to days. And then my second conversion results in the units days being eliminated, leaving me with seconds, which are my desired units. And of course, after I finish this calculation, I'm going to draw an answer around, I'm going to draw a box around my answer. Good. So we can also, so that all of those examples were using conversion factors and equalities to convert within a given system of measurement. But we can also use conversion factors to convert between different systems of measurement, for example, between the English system and the metric system. So a typical question might be express 3.25 feet in centimeters. So I know that there are 1 foot for every 12 inches, and I know, because I'm given a table of conversion factors, that in every inch there are 2.54 centimeters. So now I can set up a series of conversion factors to move from feet through to centimeters. So initially I want to convert from feet to inches, so I'm going to divide by feet, multiply inches. Use the conversion factor that has feet on the bottom line and inches on the top line, and so that's going to leave me with units of inches. And then I'm going to multiply by, I need to convert from inches through to centimeters, so I need to divide by inches and multiply by centimeters. So I'm going to use the conversion factor with inches in the numerator, with centimeters in the numerator and inches in the denominator, and then that will eliminate the unit of inches from my calculation. So that leaves me with my answer in centimeters, and so there we are, and I've expressed this to 3 significant figures because that's how many significant figures were in my initial measurement. So you will always be given any conversion factors or equalities that you require to answer the question, with the exception that I expect you to know the 6 decimal prefixes, which were micro, milli, mega, deci, centi, and I believe it was giga, but there were 6 that I asked you to learn in the last lecture, and you won't be given those, but any other conversion factors you will be given. Okay, so moving on, we're now going to see how we can use density as a conversion factor to convert from units of mass to units of volume. So what I mean by this is that if we are given the volume of an object, we can use the density to calculate its mass. And conversely, if we are given the mass of an object, we can use the density as a conversion factor to get its volume. So as we've discovered in the lab, density is the ratio of an object's mass to its volume, i.e. density equals mass over volume. So whenever we determine a density or record a density, there must be a number that determines the magnitude of the measurement. It must have a mass unit, and it must have a volume unit. Okay, so this could be kilograms, it could be grams, it could be pounds. This volume unit could be millimeters, it could be milliliters, it could be liters, it could be gallons. But we need all 3 of these components for a properly specified density measurement. So density is kind of an interesting property from a scientist's point of view, because it tells us about the some interesting physical characteristics of an object. And as we did in the lab, you'll know that we can that the density of liquids in a solid that is placed in it are related. For example, a object that is more dense than the fluid that it is placed in, it will sink. Bloop. An object that is less dense than the liquid that it is placed in will float. Now, by float, I mean it will actually sit on top of the liquid. It won't penetrate the liquid at all. And so that might be slightly different from the normal way in which we use the term float, where we think of it kind of as long as it doesn't sink, then it's floating. And then an object that has equal density to the liquid that it's being placed in will remain stationary. It's said to be neutrally buoyant, and it'll just sit in the one position. And that's what we were aiming for when we were trying to determine the density of our eggs, that our egg just sat there, not floating on top of the surface, but just sitting there neutrally buoyant, just at the top of the liquid. Okay, so this cue ball, or it's not a cue ball, this 3 ball here is clearly less dense than the beer glass of mercury that it is sitting on. So density can be used as a conversion factor to relate volume and mass. So I talked about this. Now this is really useful, because if you know the density, you can measure the mass and calculate the volume. Converse, which could be useful if you have an object that's a solid, it might be very easy to measure its mass, but quite awkward to measure its volume. Similarly, you may have a liquid, and it's very easy to measure its volume, but what you really want to know is the mass, and measuring mass of liquid is a little bit awkward. So density can be used to convert between volume and mass. So here's an example. For a given density of 1.03 grams per milliliter, that's close to the salty water that we made the other day in the lab, 2 conversion factors can be written. We could write 1.03 grams per milliliter, and we could write 1 milliliter per 1.03 grams. Either of these conversion factors is an accurate representation of what this density is telling us. Per milliliter of 1 milliliter of solution will weigh 1.03 grams. 1.03 grams of solution will have a volume of 1 milliliter. They are equivalent statements. So multiplying a measure of volume by this conversion factor will give you the mass, whereas multiplying the mass of an object by this conversion factor will give you the volume. Okay, so here's a typical example. Blood plasma has a density of 1.027 grams per milliliter at 25 degrees Celsius. So the density of liquids of all matter really varies a small amount with temperature. So it varies a very small amount for liquids and solids, and varies much more substantially for gases with temperature. So often we just say that solids and liquids have a fixed density because they don't vary much with temperature. Okay, so this question's on with this question. Blood plasma has a density of 1.027 grams per milliliter at 25 degrees Celsius. What volume in milliliters does 125 grams of plasma occupy? So we're looking to convert from grams, a unit of mass, to milliliters, a measure of volume. So this is the density, and so to go from grams to milliliters, we will need to use the conversion factor that has milliliters in the numerator and grams in the denominator. So take 125 grams and multiply that by this conversion factor here. Okay, there we go. And then that, using our dimensional analysis, we eliminate our units of grams, leaving us with units of milliliters, and this is obviously incorrect because I've recorded the mass here rather than the volume. So I'll just change that right now and see if we can edit that. And then that will be correct. Okay. Put my box back in the right spot and on with the video. So there we go, much better. We have the correct units now, except for the animation doesn't quite work. Alright, so the final thing that we need to look at is the relationship between the different systems of temperature. So there are three common systems of temperature that are used in the USA. In science, we generally use the Celsius system and the Kelvin system. But in everyday life, you might be more familiar with the Fahrenheit system. And these three systems are related not by conversion factors, but rather by formulas. So the Fahrenheit scale is offset from the Celsius scale by 32 degrees. So what do I mean by that? I mean that the freezing point of water on the Celsius scale is 0 degrees, whereas the freezing point of water on the Fahrenheit scale is 32 degrees higher, it's 32 degrees. So we need to take into account that there is a 32 degree difference in the 0 point of the scale. The other thing that we need to take into account is the size of a Fahrenheit unit versus the size of a Celsius unit. So the Celsius unit was designed so that there were 100 intervals between the freezing point of water and the boiling point of water. But the problem is that the water boils at 212 degrees on the Fahrenheit scale. That is, there are 180 degrees between the freezing point of water and the boiling point of water on the Fahrenheit scale, i.e. a Fahrenheit degree is only 5/9 that of a Celsius degree. So to take that into account, we have to subtract 32 from our Fahrenheit scale to get the 0 in the right spot, and then we have to take into account that each degree is only 5/9 of a Celsius degree. So here's our formula for converting from Fahrenheit to Celsius, and then a simple rearrangement of that gives us our formula for converting from Celsius to Fahrenheit. Should you need to convert between these two scales in a quiz or an exam, then I will give you the equation to allow you to do so. But it is very rare that we will ever measure anything in the Fahrenheit scale in the chem lab. All of modern science equipment is labeled in degrees Celsius. So here's an example: convert 37 degrees Celsius to Fahrenheit degrees. So just using my formula and substituting in, it's 9/5 times the temperature in degrees Celsius plus 32. I substitute in my 37, I perform the calculation, and here we are, 98.6 degrees Fahrenheit. So 37 degrees is near body temperature, and I know that body temperature is near 100 degrees Fahrenheit, so I can feel pretty confident that I got my calculation here correct. Okay, and again, it's really appreciated by me when you do numerical questions if you circle your final answer. Alright, so now we need to think about conversions between Celsius and Kelvin. And these are somewhat easier than the conversion between Fahrenheit and Celsius, because the size of a Kelvin unit is the same size as a Celsius degree. So 1 Kelvin unit, here's 1 Kelvin unit going from here to here. That is the same size as 1 Celsius degree. Okay, so we only need to take into account the offset, and 0 degrees Kelvin, the lowest theoretical temperature, known as absolute zero. We'll talk about what we mean by that a little later. 0 degrees Kelvin, that is equivalent to minus 273.15 degrees Celsius. So the Kelvin scale is offset from the Celsius scale by 273.15 degrees. So here is the relationship between Kelvin and degrees Celsius. So simply have to add 273.15 to the Celsius measurement. Now sometimes you don't actually need to do the conversion at all. For example, if I was told that the temperature of an object is increased by 5 degrees Celsius, because I know that the size of a Kelvin unit is the same as a Celsius unit, then this is the same as a 5 Kelvin rise in temperature. Okay, good. Alright, so doing an example here of converting between Celsius to Kelvin, we can see we're asked to convert 372.35 degrees Celsius to Kelvin. So this is our formula that we are given. We can rearrange that to get a formula for calculating Kelvin, and then we just have to substitute into the equation. So Kelvin equals degrees Celsius plus 273.15. So this is what we're given, 372.35 plus 273.15 leaves us with 645.50 degrees Kelvin. Okay, and then it's appreciated by me if you circle your answer. Okay, so that concludes today's lecture.